Okay, everybody. Hi, everyone. Welcome to today's webinar. Today's webinar will be comprehensive analysis and design, all in one place with Oasys GSA. I'm Andrew Eckert, Business Development Manager for Oasys, and today our presenter will be Peter Debney. He's an application specialist, an engineer, and a fellow of the Institution of Structural Engineers. Now, at the end of today's session, there will be time for all of you to ask questions. So what we would ask is that during the session, if you would please place your questions into the Q&A, or alternatively, if you don't have access to Q&A, please put your questions into the chat and we will move them across. And we hope to be able to answer everyone during today's presentation. But if we can't, what we'll do is we will look at your questions and we will get back to you via email. Okay, so what we're going to do now is I'm going to hand over to Peter Debney and the webinar will begin. Peter, over to you.
All right, thank you very much. Can you see my screen okay? Is that sharing?
I can.
Actually, okay, wonderful. All right. Okay, well, let's get going then. Yes. Oasys, quick introduction to us. We are engineering software and we cover a range of engineering products and product types: structural, geotechnical, and pedestrian motion, or pedestrian modeling or mass motion, the main ones, but we do have some others as well. And so we're looking at structural, and in particular structural we have GSA, which we're focusing on today, but also ADSEC, Compost, and ADC for looking at concrete sections, concrete beams, columns, composite beams, and so on, all in more detail. We also have the ecosystem of our products, so the Speckle and Revit connections, but we also have 3 Grasshopper plugins for GSA, ADSEC, and Compost, and we'll be having a look at those in a bit. So GSA itself. What's GSA all about? Well, GSA is a general purpose structural analysis and design program, which has been used in a huge variety of iconic structures around the world. For example, the Swiss Re or St Mary's Axe, in London, the Gherkin, Marina Bay Sands, the Helix Bridge, and so on there in Singapore, King's Cross Station in London, the Infinity footbridge in Stockton, a winner of the Institute of Structural Engineers Supreme Award 2009, I seem to remember. The London Olympics, ArcelorMittal Orbital, the main stadium, the Aquatic Centre, the Velodrome, and the Shooting Gallery, and a few others. Anyway, yeah, most of the London Olympics, and so on. So the basic tenets of GSA are transparency, flexibility, and power. Transparency, yeah, we give you full access to all the information. You're able to see all the results, why we give the results, and give you power and control over exactly what the program does. And yeah, so you can do things like you can work in the graphical view, you can work in the tablet view, both at the same time. You can work with APIs to integrate directly with the program and so on. And yeah, this all adds up to a lot of power in your hands, which also means we got static, non-linear, dynamic analyses, and goodness knows what else. Anyway, we have a look at the a few of the highlights of the program today. So some of the USPs: editing control. Yeah, we can edit the model in many different ways. The meshing abilities in GSA are incredibly powerful and interactive these days. Blocks for creating structures quickly. Draw one floor, just repeat it as much as you need. Volumes for editing, see exactly what you need. Assemblies for taking overall structures like cores or composite beams and so on, and just condense them down to just give individual results. The analysis options: stability analysis. Something's gone wrong. What's gone wrong? This tells you. Footfall for human-induced vibrations. Imperfections for Well, not notional horizontal loads, but what causes notional horizontal loads. Powerful nonlinear analyses and form finding analysis. And the post-processing, all the results there, all in one place. Steel design, soil structure interaction, APIs, application programming interfaces, and the GSA and the plugins into Grasshopper as well. Anyway, yes, workflows. How do you work with it in general? Yeah, you can create your model in a whole variety of ways. Work in GSA and then export the results in a huge variety of ways as well. This is all sort of a classic workflow, how you might work with it, but you might be more modern and have a speckle server as the central control of the whole project, of which GSA is then the components. Or you might decide that you're going to work with Grasshopper as the central element in your structural design, then interacting with the architectural models and so on. Right, at this point, I am going to jump over to GSA itself and take you through actually using the software. So this is live. This is dangerous. Here is a blank model. I have set up a few things, some grid lines and grid planes and a few properties. Anyway, right. So here we have our basic model. What I'm going to do is I am going to change to the first floor grids, and I'm going to start adding some beams in. So what beams are going? On the generic, let's say our primary beams. Let me just change down to the basic grid. 3 beams there. Draw them again. Let me just copy them up. Copy, let's say 3 copies at 9 meters. Preview that. That's all good. And then the secondary beams could do the same thing, but instead what I'll do is I'll just grab those points, draw the line in. Let's actually color code just to make sure we're coming in correctly. Yeah, that's all good. Add the secondary beams in. Okay, we've got the main frame going in. Let's also add in some columns. To just grab the outside nodes, and rather than copying, I'm going to use an option called extrude. Let me see, 1 increment minus 4 meters, include members, preview that. Adding the columns, and we also want all the rest of the secondary beams, which we haven't got yet. And copy these in. You see 2 copies, 3 meter centers. Wonderful. Now, now in the middle, we haven't got columns in the middle. We're going to put a core in here instead. So what I'm going to do as well is just take those middle beams. I'm just going to turn them down to a shelf angle to pick up the loads from the floor onto the core. And then I'm going to use the extrude command again. And this time, rather than columns, I'm going to create walls instead. We run extrude. There we have it. So outer core. What about the inside walls? Let me just reduce the display down to the 2D members. Copy that one up. 2.5 meters. Do the same there, but in the opposite direction. And oh, how do we get into the core? Let's create an opening. So I'm going to select the node there. I'm just going to copy that up and construct 2.1 meters up. Okay, do the same again, copy them over. 8 meters, and I'm going to draw in not a wall or a slab, but a hole, a void cutter. So this is a void cutter. It just cuts a hole through 2D members, and then I'll just move it up a bit into the middle, and you can see the meshing is all adjusting around that. Now, at the moment, we've got a 1 meter mesh. It's a 200 thick wall. I'm going to reduce it down to maybe half a meter, and there we have, the core is ready to go. Oh, also, of course, this is a steel frame. What we need to do is make sure that we have moment releases on the ends of the beams. So what I'm going to do, right, property beam, look from the side, select all those beams, and then just add in moment end releases in the major and minor axis direction, but not the torsional direction. Connections do have a torsional stiffness, and we don't want to destabilize the structure. Okay, all good. Now, also, of course, if we're not modeling the floor in, well, let's do model the floor in. Let me go and add in the floor. So 2D generic, put in the slab, run around the outside, enter to close, and we have the slab. But actually, rather than modeling the slab itself, what I want to do is PA2. What I do is I'm going to turn this rather from a slab into a rigid diaphragm with a large mesh size. So it just stabilizes for it, acts as the slab without adding any stiffness in there. Now, mentioned about meshing. Let me switch to PA to show everything apart from that slab. Yeah, the mesh. Yeah, the members automatically recognize each other. And what I can demonstrate this by adding in, let's say, yeah, if we were to put a beam straight through the diagonal through the core, where does that interact with the walls? Well, you see, they automatically detect each other, and you see if I look in the Y direction, you can see automatically meshing together without you having to work out where those coordinates are. And similarly, if the beam is, say, in the plane of the structure, you can see it is automatically meshing. Let me just show that in a bit more detail. Yeah, very, very quick and easy. Let's get rid of those. Back to where we were. Okay, right. I think we've got enough to work with this. So let's switch over to the analysis layer. And save the model. And I'm going to create elements from the members. And the strengths. Let's put some support points down the bottom. And we also need, of course, some loads. So I've got two load case definitions out, dead and live. This means we just add in some actual loads. So self weight of everything, automatically calculated from the section size and material density and so on. But for the live loads and dead loads, we're going to use grid loads, and I'm going to grid area loads. Let me tuck that down to the bottom. And then I'm going to say, okay, on the first floor, the whole plane, dead low case, let's say slab and super dead, say -4 kilonewtons, and then the same again, but live load and say -3.5. So we can see these. So here we have the self weight and the overall grid load, and also the live grid load. Now these grid loads will automatically expand onto the beams when we analyze. So let us analyze that now. And we have a problem. It starts to analyze and it says there is a singularity, ill-conditioned model. There's something wrong with our analysis model. What have we done wrong? Okay, so for this we have a model stability analysis. This is designed to look for areas of zero stiffness in the model. Therefore, what's not connected properly? Let's analyze that. Or error norm e to the 43. That's a definite mechanism. It's complete. Let's have a look. So we have an output for this, global results, model stability, and we see, yeah, we've got lots of issues, very high condition number, and look at results. So there are a couple of ways of exploring what the issues are. In the contours, so in general results, I can go, let's say, virtual energy and see, okay, there's something wrong with this column. And all I like to do is look in nodal results. Maybe is it translation? Nope. Rotation. Now the column is spinning, it's rotationally unstable, and that is because we have moment releases on the ends of all the beams and a pure pin base on the bottom of the column. These columns are torsionally unstable. So let's delete those results. Get rid of the analysis case, and then I'm just going to display just the beams, and get rid of the contours as well. And add in a ZZ restraint onto those columns. Now back to static analysis. I'm gonna run that, and yep, it has run fine, no errors. So what do we get in the results? Well, as you expect, bending moments, shear forces, contours, so axial load in the columns, and so on. And you notice we can display all of these simultaneously. We might annotate some of them so we can see the values. And so we can get all the 1D element results out. But let's look at the core property area one. Get rid of the shrinkage, and it's one of my favorites. I'll just use a volume to look at this end wall here. So under the diagrams, one I quite like is we like the principal stresses. So you can actually see how the forces flow through the concrete. Let me just average the nodes so we can see a bit clearer. Yeah, you can see that those lines of force passing through the structure. So, of course, we also get the 2D results, of course, as well, and so on. So basic analysis. What other type of analyses do we have? Let me go and open up a model, very simple model. Looking at footfall analysis. So this model is set up slightly differently in that I've ensured that the walls and columns go both halfway above and below to the next floor. I've also set up, actually, let me call up again, and you see we've actually got offsets set on the beams and slab. So, for example, the slab there, it is modelled with decking, and it's set to the bottom. Decking options are made available, and similarly in the beams, we have the beams offset to the top. Now, I would recommend against doing this generally, but when it comes to footfall analysis, when we want to get that composite action between the slab and the beams, this is definitely the right approach. Okay, let's switch over to the analysis layer, already meshed. And again, we need some restraints. Now, footfall analysis model, we've deliberately not put in end releases on the beams. I will pin the columns and core top and bottom, and then also property area 2. I'm also going to add in cladding restraints, so Z and X, and that direction Z and Y. This is the effect of the cladding. So in footfall analysis, the cladding restrains the slab rather than the other way around. Okay, this stage, let us add in a modal analysis. So modal dynamic analysis will find all the natural frequencies of the floor. Now, footfall analysis, we need up to 15 Hertz. Not showing modes. I'll ask for 20 modes, but I'll have a frequency cutoff of, say, 15 Hertz. So we won't fill out the model with unnecessary modes. Mass at nodes, add in mass derived from loads, dead and live, but as traditional, only take 10% of the live load. Analyze that. And we can see no horizontal movement, just on the vertical. That's fine. I'll look at the results. 12 modes. When we asked for 20, only got 12. So we know that we have got cutoff level at the right point. Let's look at the shape and the contouring displacements. So we can see we have mode 1, frequency of 8.527 Hertz. Next one, very similar, 8.530, very nearly the same frequency, but not quite. We've actually got a slightly asymmetric model due to the fact of the opening in the core. This does affect the difference in stiffness on the floor, and we can see we do have a number of closely set modes. So what are these? So mode 2, mode 3, 4, 5, 6, 7. Yeah, as you expect, all pretty similar. Do we have enough modes that we've captured all the bays? Let us find out. What I'm going to do is I'm going to do a quick combination, which is an envelope of modes 1 to 12. Name it, but and then just force that to yeah, I think we've got enough modes in there to capture all the important parts of the structure. Okay, the modal analysis, that's the basis. Now what we want to do is add in a footfall analysis. So footfall, human induced vibration. I'm going to do is a full excitation. Response and excitation nodes, I could just take just the slab for speed. I'll do the whole thing. Number of footfalls, footsteps. It's 27 meters long, divide that by 0.7, 35, 40 steps along the length. Weighting curve, concrete center, SCI methods, etc., AIC methods, American, yeah, lots of options we put in there. Damping, and let's just analyze that. Okay, whole model, 1 second. That's fine. Let's go look at the footfall results. And so under footfall results, we have yeah, the various velocities and accelerations from resonance and transient results, and the summary. So we've got the transient up to about 6, the resonance up to about 12, and then the overall maximum. You see the slight, transient is slightly dominating in these areas. Now this is the nodal results, but it's easier to read them if we smear them over the 2D elements. And yeah, there we have the overall results. This is automatic contouring, but let's change that, and maybe we want to set the contours directly. So we go 0, 1, 2, 4, 8, 16. Classic response value values, and you can see, if our target was 8, for example, then parts of the floor are okay, parts are a little bit outside the requirement. So at this point, we then start to review the design and see how we can sort that out. Okay. What else can we do in GSA? We can look at soil structure interaction. So in this model here, again, very similar to before, but this time what I've got in here is a soil model. So this soil model here in the raft area, this is essentially, it's a PDISP model. PDISP is our pressure displacement of the ground model, and so we've added in some soft clay stratas over stiff clay over dense sand and gravel, and you see the stiffness is gradually increasing with depth. And I've got some basic and what the raft analysis do, basically we'll add in spring supports under all the corner nodes. Let me switch on the raft interaction area. So what we've got here is we specified there's a number of nodes which are interacting with the ground, which are all the raft parts, but not the superstructure. Let me switch those springs off for a minute so it's a little bit easier to see what's going on, and switch the grid off also. Yeah, so we've got these parts of the structure interacting with the ground. You notice I've set that actual elevation, which is, it's a 1 meter thick raft. So offset the interaction down, and I also have loads in the from the superstructure. So decided so we don't need the superstructure so much in this model. It's the stiffness of the raft that we're interested in rather than the stiffness of the superstructure. And so these values are sort of some quite high column loads and so on coming down on here. So at this point, let's analyze this. So what I'm going to do is I'm going to add in a raft analysis. To the nearest 1 meter. What it's going to do is going to iterate between GSA and PDISP and get to give the same displacements. I'm going to create my loads. load, and let's quickly look in the advanced options. That's all of the analyses. We have the sort of advanced options. You can go in and fine tune things. So things like initial support stiffness, raft analysis. If we haven't got spring set already, follow progress, save the soil stiffness after the analysis, imperfections, and what results do we need. Anyway, that's all good. Analyze that. Now, it takes a moment to set up. First of all, not just got to create the stiffness matrix, but also the flexibility matrix, how the soil works with the structure. Once it's done that, it'll then start iterating, analyze GSA model, get the reactions out, put those pressures into PDISP, get the soil displacements out. This will give new spring stiffnesses, put back into GSA, and iterate between the two until it's finished. So what we now have is updated spring stiffnesses and structural displacements, for example. How much is it displacing? Nearly 60 mil in the middle. Reasonable amount. What else do we get? Well, we could look at reaction values, but of course the reactions are also dependent on the element size, so this is not ideal. What we want more interested in is the soil pressures. What is the contact pressure between the raft and the soil? This is directly on the nodes, of course, and again what I can do is display that those pressures directly onto the raft. And of course, because we've got the results, then we can also look at the moments in the various directions. Let me MX, MY, and let me just we could look at maybe just the center values, which are the more accurate, or we could look at the average to give us a more smoother contour. So moment in the X direction, Y direction, torsional direction, and then torsional direction, torsion the slab, and then also the wood armor moments for reinforcement design. Okay, there's rafts. We mentioned assemblies. So here we've taken the lift core from the model earlier, given it the full stack, and I've added in some assembly. So what assembly does is it takes all the results on the model. Let's say all the displacements, all the stresses, and so on, and it integrates them all together to give one overall results. This will have assemblies, and we see I've got an assembly down the middle which shows the overall results, but also got an assembly on just the wall there. So what we can see is let me just switch on the assembly axes and look at the assembly results. So for example, we can look at the displacements of the wall and structure. We can look at the moments. Let me just take that down to just the central assembly, so we can see that a little bit clearer. Yeah, so we can get all the various forces and moments. So this is what's the overall force on the core, what's the overall bending moment on the core, and so on, and condense that down to just single values that we can then work with. How do we set these up? Well, quite simply, let me open up the assembly table. Tuck that at the top. Now, what I've got define. Let me switch layer. Yeah, what we want to do is maybe look at one of these sort of lintel areas. Now I do have a list set up. So what I'm going to do is I'm going to call up a before I do that, let me just get in here and switch on the node numbers, because we need not just the elements in the assembly, but also what is the axis of the assembly itself, and we use nodes for this. So I'm going to say it's going to be the lintel. It's going to be an element assembly. The list, I could select the screen, but let's take it from here. Topology, maybe start from that middle node there. 10429 to 5485. Orientation node, which way is the y-axis going? Let's say to node 10. Automatic extents and so on. And there is our lintel. Let me just volume down to get to that. Anyway, so here we have our lintel assembly, and again we can get out things like the moments and shear forces and so on this as before. And basically what this is doing is it is just integrating all those stresses in the structure and converting them into the overall bending moments and forces, which they don't really exist, but they're a useful fiction. Okay, right. Let's have a look at steel design as well. So again, our model, back to the rigid diaphragm, and now in this instance, rather than just having the two sections for the structure, what we're actually going to do is add in lots of steel sections, which GSA can then choose from. I'm just going to delete out those two. I'm going to add in many sections of British steel, universal beam, select them all, but exclude those ones with the narrow flange. We want enough flange to allow the planks on everything. And I'm going to put these all into pool number 1. So basically all the members in this pool will choose from any other section in that pool, and so we have one pool for the beams, one pool for the columns, for example, and there we have lots of beams. Now it's picked up the section profile directly. I'm just going to tweak that. Search replace cat bs hyphen place with blank, not entire cell. Place it just in that selection. We don't want to do it in that section profile column because that would stop the analysis. So this is just the name field. Much simpler names. Okay. So at the moment everything is very chunky. To update the elements from members, run the analysis, all is set up, ready to go. So here on design layer, and then once again we do have all the bending moments and so on. So design of these sections. Now I put all these top beams into group 1. And if we look at the steel design, so design codes, many different international codes. I've got the British Euro codes, but yeah, there are many codes in there. And we do have some standard design criteria, such as how the members interact with each other and so on. So if we look at the steel design utilization, currently everything is coming up black, infinite. We need to set some design parameters on these. So I'm going to select all those, and yeah, design effect options. End restraints, it's free at both ends. No, they're going to be pinned at both ends. We're now getting some calculation done. Currently everything's got a very low utilization, but that's not surprising. They're very big sections, and we can see, yes, we do now have some utilizations going on. At this point, we could design them, but let's look at the other design options. So currently everything's automatically calculated, but we can choose to maybe say directly specify the effective lengths. I've got everything selected, and at the moment it's just picking up the overall lengths, and you see these prime beams slightly shorter. Or I could say specify the internal restraints and say top flange is lateral restraints, at the support points or the connection points, the primaries, top and bottom flange restraints. And now I'm going to do is set up a design task, which will go through all the beams. Group 1, use the combination case, maybe push the beams as hard as possible. Size by weight first of all, then maybe depth second if they've got two sections of the same weight. And what I'm going to do is going to actually run that task. I should have done, of course. Show the section sizes. So the section sizes are now updated. And we can see that yeah, we can see from here everything's running pretty close to I've got some infinity, but that's sections we haven't actually designed, so I'll exclude those. Everything's running pretty well. Let's go back to the contours. Yeah, and we can see that everything is running at very high utilization, which is just how it should be. Right. And we are out of time. So what else can we do with GSA? Yeah, mentioned APIs. So we've actually got two APIs in GSA. The old COM API, which sort of interacts directly with the GSA interface, whether it's showing or not is there, and then the modern .NET API, which interacts much more directly with the GSA engine. So it is considerably faster. In fact, this is what we're using in the new Grasshopper plugins. So yeah, so for example, so the GSA Grasshopper plugin, this enables you to run GSA directly within Grasshopper, but also enables you to save the models out afterwards. It gives you the access to all the editing commands. As we can see here, even things like the meshing. Now, you know, those who use Rhino, the meshing of Rhinos is not really good for FE analysis, but GSA's meshing is, and so this is defining the models, and this video is in real time. It is a very fast and how it actually calculates all those interactions automatically. Likewise, there is an existing model. Let's go and open up the model, add it into your Grasshopper script, edit it as appropriate. and then save it out and reopen it back in GSA as edited. So yeah, whistle-top tour of everything. Yeah, do we have any questions?
Right, Peter, we do have a few questions that have come through. So I'll start to run through them with you now. The very first question being, can Oasys be used for research? And I think I can answer that one. I mean, it can be used for research, and we do make GSA licenses available for academic research. The thing to do there would be to get in contact with oasys@arup.com, and we can discuss with your university administration how you can all get access to it. Now, our next question, do I need GSA to run GSA Grasshopper? Peter?
Yes, you do. So the Grasshopper plugin uses your GSA license, though I think you need to have a GSA building license or above to run the plugin. But yes, it all connects automatically.
Okay, and once again, for anybody who needs to get to the GSA building end, if you email us at oasys@arup.com, we can discuss how to do that with you. Next question is, can complex 1D sections modeled in, such as built-up sections, extruded profiles, etc., also, what other material designs are supported apart from steel?
Okay, two questions. So first of all, sections. Yeah, I mean, with the sections, you have a huge choice of options. So you can, yeah, use the steel catalog sections as show there. You can use a parametric section, say, I've got an ice section, what are its dimensions? And so on, all many different shapes. Or you can set up perimeter sections where you define the outline directly, maybe with a DXF import or coordinates, thin wall sections, or even, you can even set the parameters directly to say, okay, this is my bending stiffness and so on. So yeah, there are many different choices about how you define the sections. Oh, what was the second half, Andrew?
Second part is, what other material designs are supported apart from steel?
Okay, yeah, so in GSA we include steel, concrete, timber, glass and fabric materials, but for analysis and on design aspects we have steel and concrete walls and slab designed.
Okay, great. We have another question now. I think Aditya's just written an answer, but if perhaps Aditya can jump in and answer this on camera. Is there the possibility of creating local mesh refinements? If yes, is it possible to choose the preferred mesh elements in the solver, triangles versus quadrangles? Over to you, Aditya.
Yes, so the answer to excuse me, the answer to both your questions is yes. You can refine your mesh locally if you have to at any point. So that if you want to find a mesh around intersections, or if you are considering cutouts and you want some custom mesh sizes around there, everything is possible. And yes, you can model triangular elements or quadrilateral elements. Both shapes are possible. And even within triangle and quadrilateral elements, you can choose between linear elements, which will be in the case of a triangular element made of 3 points, or you can choose a higher order element, which will have 6 nodes and have quadrilateral shape functions, for example. So yes, all your questions and more are possible. Yeah.
Terrific. Okay, the next question. I've already got an answer for this. Which form finding methods does GSA cover? Is the soap film method included? The quick answer to that is yes. It has soap film and force density methods. Both are covered within GSA. Right, our next question is about soil profile. Is it possible to set the soil Young's modulus as a function of depth within a stratum? Whoever wants that one.
Yeah, so basically, you specify the Young's modulus at the top and the bottom of each strata, as required. And if you need a more complex, if it's sort of not quite such a linear profile through the strata, you just break the strata up into different sort of different layers as is appropriate.
Okay, terrific. Next question is about raft analysis. So where do you get the spring stiffness data from when doing raft analysis?
Okay, so the spring stiffness actually comes from the analysis itself. Now, you might have an initial estimate, but that actually makes no difference to the final result. That just speeds the analysis. So what happens is that GSA will work with the soil model and from the soil stiffness combined with the structural stiffness and how they interact with each other, it will iterate until it calculates the spring stiffnesses at each point across the structure. And where you find that you'll get much higher stiffness towards the edge than the middle, and so on, due to the stress bulb effect. So it's an automatic calculation.
Okay, the next question then is, can I make groupings in the steel design optimizer? Is it possible for a group of beams or columns to be assigned to the same C/S Dunning optimization?
Yeah, you can set up as many groups as you like within the steel design. Now, whether you should or not is another question. That's an ongoing debate in the industry at the moment. Personally speaking, I would say don't group them and then discuss grouping with the fabricator directly. But yes, grouping is indeed an option, which is fully under your control.
Okay, the next question is, how can we get access to the example files that you're using, Peter? It would be great to go over the webinar in our own time and to explore the models further.
Yeah, I'm happy to share the files with you afterwards. They're just standard GSA files.
Okay, if the person who asked that question, just drop an email through to oasys@arup.com and we'll arrange to get those examples out to you. Right, somebody's asking where they get the Grasshopper plugin from.
Yeah, so you can get the plugin. I think this was answered before, that you first need GSA to be able to run the GSA Grasshopper plugin, and you need at least build 10.1.60 and above. And once you have this, you can get the Grasshopper plugin from Rhino itself. Just type package manager in Rhino and search for the GSA Grasshopper plugin there. Make sure to check the include pre-releases boxes, and you should see the plugin in the in the dialog box there where you can download it from. What I'll do now is drop a quick link in the chat which shows how to do this exactly, so that you can do it, so that you have a visual reference. Yeah.
Okay, I'll move on to the next question. So this concerns the first example. It says, even though the columns are pinned to the beams, does GSA apply an, I think it's eccentric moment from the connection? And the example they've given is half the column width plus 0.1 m beam
yes.
shear load.
So yes, GSA can do. So in the model there, I added in end releases, but I could have also added in automatic or end offsets, which would have shortened the beam by half the column width plus an additional value as appropriate, and that would then automatically add on the eccentric moments onto the columns. So yes, you can do. It's up to you to set that in the model.
Okay, great. We have another, I think another question from the same person. So this is concerning the footfall analysis. So some documentation assumes all end connections are fixed. Is there a reason why the example shown did not fix the end connections?
in the example that I showed just now, I did have the end connections fixed. The reason for that is under a footfall analysis, the strains are very small, which means even with a bolted connection, the friction within the connection is such that you don't actually get any slippage, and therefore they are effectively continuous. Yeah, and so in that model there, they were continuous.
Okay, great. I think that answers that question. Next question is concerning raft analysis, Peter. Does the user need a PDISP license and or a PDISP installed as well as GSA?
No, the PDISP engine comes with GSA building and above, and that is fully included. If you want to export the results into PDISP and then look at that directly in the PDISP engine itself, then do things like look at the soil stresses in the soil mass below and look at the effects on buried surfaces and that sort of thing. Yes, for that you do need a PDISP license, but for the raft soil structure interaction, no, you don't need the separate PDISP license.
Okay, great. The next one's concerning temperature analysis, Peter. So temperature analysis or thermal analysis, can that be carried out using GSA?
Yeah, definitely. We have thermal loadings, which can either be sort of a uniform load or a cross-sectional thermal gradients. Yeah, and obviously that you then got the coefficient of thermal expansivity set into each of the material grades. So yeah, it's all there.
All there, quite comprehensive. Great. And can you do pile on raft analysis stroke design?
That's right. Yes. So we can also include piles under the raft. So we model the piles explicitly with the sections. Time is quite short. The pile analysis is a bit more non-linear, so that takes a longer to run. But yes, you can then set up all the pile soil interaction coefficients as appropriate with the granular and cohesive soils, and then run it with the piles as well. I mean, Crossrail example is quite a good example of a piled raft analysis. There were some major station boxes designed using GSA on that project. Also, not Crossrail, the Elizabeth line, as we should call it now.
Ray, there's another question from the same person again concerning raft analysis. Does raft analysis can it include the stiffening effect of core walls?
Yeah, so in that raft model, I did actually include the core walls up to the first floor level. So yes, you can include them as much as you want. In this instance, I model them explicitly, or you could put in beam elements which give the core wall stiffness. Yeah, it's entirely in your call. You couldn't even model the entire structure, but it's probably not worth it.
Okay, right. And the final question for today is it appropriate for hybrid building as well as traditional building built by local communities?
I mean, GSA, yeah, who's building the model who's building the structure doesn't really come into the model. So GSA is a elastic plastic analysis, so it is fully appropriate for steel, concrete, timber. You can use it for masonry as long as the stress levels are reasonably low. Masonry is as we can see, masonry is sort of compression only, so doesn't fully align itself with finite element analysis, but you can use it to some degree. But so yes, but it is, yeah, you are the engineer. You can choose to use GSA how you want and make sure it is valid. So yes.
And I can complement.
Sorry, go on, Aditya.
I could complement the previous answer with that, especially like if by hybrid building, if you mean building on top of existing structures, or if the traditional building applies, that you have some non-standard geometries. I just want to point out the Grasshopper plugin for GSA can also be a very good fit for your use case for either building on top of existing buildings, or for having some non-standard geometries, or just having some more freedom with editing the geometry in general. So the Grasshopper plugin can definitely be useful in this case as well.
Yeah,
Okay,
and
we
also,
just
of course,
had one. Sorry, go on.
yes, and of course you've also got the stage analysis, so you can analyze the sort of the stress state of the existing structure, and then add on the new structure, so you can then see how that changes between two. So you can look at construction sequencing, but also sort of adding on and refurbishment, adding and removing loads to existing structures. So yes, so that is all capable in GSA.
Okay, we've had one last question that's just slipped in. Does GSA do pattern loading stroke checkerboard?
Okay, so pattern loading, yeah. So I mean, in terms of checkerboards, yeah, you can define checkerboard loading directly yourself. We do have a pattern load optimizer, which is actually much more comprehensive than checkerboard. Checkerboard is okay for sort of like 1D approach. The load optimizer is good for full floors. And so yes, indeed, you can do that.
Okay, well, that appears to be the end of the question and answer session. So that will also bring today's webinar to an end. Before we go, we'd just like to make clear that you will be able to pick up a recording of this webinar here in the meeting chat. But if you don't get to it in time, do drop us an email and we can send out the recording to you if you think it'll be useful for the future. So thank you all for coming, and I think we'll say goodbye at this point. And thank you, Peter and Aditya, for presenting today.
Okay, thank you very much.
Thank you.
Okay, bye now.
Bye-bye.